This project is about embedded controller on an ARM Cortex-M processor. It has two applications: robust suspension and inverted pendulum on a cart. The processor is STM32F4 and I use Kyle Macrovision 5 to develop the project. As a programming language, I use C++14 to implement the algorithms. Unfortunately, Kyle Macrovision 5 does not officially support C++17. The FreeRTOS is the real-time operating system in this project, and for communication between embedded device and PC, I use TCP socket to send and receive data. The library that I've chosen to use for network programming is LWIP. Also, the project has various types of tests that I will show them later in this video. This is the source code of the project in the Kyle Macrovision 5, including C++ classes and header files. Also, there are some classes for testing the application. If you want to run the unit test, you have to define test env for the project. If I run the application, you can see the results of the test in the console. There is no need to run the integration tests on the hardware. I run them on my Windows. First, I have to build the project. Then I can run and see the results. For more information about the test, you can see the README of the project on GitHub page. This is the application of the inverted pendulum on a cart. It is based on an example from Data-Driven Science and Engineering book written by Stephen Brunton. At the top you can set the IP and the port of the embedded device, and below them you can set the angle of the pendulum. After setting the parameters, I can run the application. You can see the result that the algorithm tries to hold the pendulum vertically by moving the cart. Also, we can replay to see the result again. Or we can reset and change the angle to see other results. The second application is for controlling suspension. I assume that we have a bump on our road. We can set the parameters of the road, the length and the height. If I run the application, you can see the results. Here you can see the difference between active and passive result. If I press the replay button, I can see the result multiple times to analyze it better and compare each situation. Also, I can enable or disable the showing of each suspension. For better intuition, the application shows the timeline. Each line shows 50 milliseconds. So if you can see the result carefully, you can observe that the active suspension took less than 400 milliseconds to reach the steady state. But the passive suspension took 5 seconds or even more. It depends on the length and the height of the bump.